Hey, my name is Leonard Palma,
My name is Carlo Maldonado.
and we are Group 6 for our measurements project. We're going to be talking about the Eddy Current Tachometer, which was our final project for this semester.
So the background information about a eddy current tachometer is that it is a non-contact device that is used to measure rotational speed of a shaft or a disc. That shaft rotates with a magnetic disc attached to it, which creates a magnetic field inducing eddy currents to an opposing conductive material. That rotation creates a braking torque that is proportional to the rotational speed, which is then transmitted to a potentiometer. Eddy current tachometers are most commonly used in vehicles, industrial machinery, and applications where reliable speed is required to be tracked. The theory of the device is that we have a motor that has a 3D printed disc on it that have magnets attached to it, which rotate, creating a magnetic field. As the rotational speed increases, so does the strength of the eddy currents. On the other side of the magnets, there's an opposing aluminum disc, which is then reacting to the eddy currents, causing rotations. Those rotations are picked up from a potentiometer attached to the aluminum disc and are then transmitted to an Arduino, which help us find the RPM.
So the implementation of the device is we had a motor shaft, mostly 3D printed, and then we have potentiometer shaft as well, which was 3D printed. Most of our stuff was 3D printed, and um, we had a pointer and digital or this analog signal printed out so that we could have analog RPM measurements along the shaft. So we also had an elastic string as well, which was helping the aluminum disc to rotate back to its original position. And we'll talk more about it on the next slide. So for the motor shaft, we 3D printed an upper and a lower shaft so that we could adjust the position and the angle of the motor itself. It was designed in such a way so that the motor could have the minimum vibration and displacement whenever it was rotating along the magnetic disk. So the potentiometer shaft was designed in such a way so that it has a position to have a bearing, which is right outside of the potentiometer shaft, and inside it has enough space to have a coupler, which is attached to the steel rod and potentiometer shaft or the potentiometer. So the steel rod is connected directly to the aluminum disc, which moves along with the eddy current. And this is calibrated or this is measured by the potentiometer, which is attached to it. We used Arduino Uno R3 as our electrical component to measure the RPM, which is converted from RPM to different torques and angles, and that is displayed on our device. We use the DC motor, which is 3,500 RPM instead of 7,000. It's because we used a 12 volt by 3 volt, 3 ampere adapter, which resists going up to 7,000 RPM. And we used that motor to directly attach to the magnetic disc, which spins along with the motor. So whenever we change the speed, the magnetic disc runs along with it, and this creates an eddy current, which creates different torques for the aluminum disc. We use the speed control for the motor. Instead of RPMs, we had displays of percentages. It helped for our design a lot in this sense. We could understand how far we are going instead of relying with RPMs. We also have a safety switch for emergencies. It's because we were having problems with having higher RPMs with the magnetic disc that gets in contact, unfortunately, with the aluminum disc. So that's why we set our percentage to 80%, and we have a safety switch to have a sudden stop if we need to while we're calibrating it. For the calculations, as eddy current tachometer is a very simple relationship we have is with the drag torque, which is proportional to the rotor speed. We also have different angular speed, which is then converted directly to angles. We also use this so that we could have accurate coding in Arduino so that we have accurate results of different torques and different angles with the RPM we are calculating. And this is just a relationship to show that, okay, the spring that we are supposed to use, unfortunately, we have an elastic string, but it still gathers the correct information or the correct relationship along with the spring. So we had a torque relationship and an equilibrium where we calculate the angle in each torque.
For calibrating our tachometer, we used a slow motion camera to capture the rotations. So that camera was our phones and set to slow-mo. And with the slow-mo, we captured one full rotation and calculated the RPMs through that. When we found the RPMs for that set percentage, we would implement it in the code to say that that percentage was equivalent to that RPM. And we repeated these steps multiple times with different outputs to ensure that our results were accurate for each different power output. And once our testing was and calibration was completed, we attached the gauge to the tachometer in the front to show the speeds that we found to match with the pin on the front. In conclusion, our eddy current tachometer was successful and it was working as a tachometer. Our calibration was efficient, but it was never 100% accurate. And we learned that the power output of the motor should not have exceeded 80%, or the high speed vibrations would cause contact with the magnets and the aluminum disc. So it was best to just avoid 80% power or more. Here's our bill of materials. The only thing to point out here is that we were not able to use the LCD display, but other than all of this, we were able to stay under budget and the project was a success.
Thank you so much.
Thank you.